governments prioritize funding genetic research to develop climate resilience crops over other agricultural innovations. So we prepared this with my colleague Juliet from Tanzania. As an introduction, as the world faces increasing climate challenges, ensuring food security has become a top priority. Climate change impacts are becoming more intense and frequent than ever, as the observed impacts of climate extremes on Africa have increased. In this context, genetic research offers a powerful tool to develop climate resilience crops through conventional breeding techniques, molecular breeding methods, genomic and transgenic approach. The governments have a responsibility to address the problems of food production and consumption, as well as to encourage responsible investment in agriculture through innovations. While there is considerable progress in the adoption of technical, institutional, and systemic innovation in the agricultural sector across the continent, genetic modification has emerged as a powerful tool in modern agriculture, offering the potential to develop crops that are more resilient to the diverse effects of climate change. For the opening statement, we can say that climate change threatens the very hard work of food production by increasing the frequency and severity of extreme weather events and decreasing agricultural yields, thus reducing the productivity. This work argues that governments should prioritize funding genetic research for climate resilience crops over other agricultural innovations because of its potential to provide sustainable solutions, maximize productivity, and most importantly, climate-resilient crop varieties will mitigate billions of dollars of agricultural production losses. Among the constructive argument for this, for climate crop resilience, we have improved nutrition. So genetic modification can be used to enhance the nutrition content of staple crops like maize and cassava, providing essential vitamins and minerals to combat malnutrition. The biofortification of crops using CRISPR-Cas9 resulted in improved nutrition profile, including increase in starch, protein, vitamin, and oleic acid content of cereal crops such as rice, maize, and wheat. We have the case study from the International Institute of Tropical Agriculture and the National Agricultural Research Organization in Uganda that used CRISPR-Cas9 to edit the genome of mother spp to modify genes involved in provitamin biosynthesis. Another constructive argument for crop resilient climate, we have the improvement of abiotic stress tolerance. The major challenges that African agriculture is facing are increasing droughts, water scarcity, flooding, poor soils, and extreme temperatures due to climate change. However, most crops are not tolerant to extreme climate environments. The aims now in Africa with hunger and an increasing population is to breed and or engineer crops to tolerate abiotic stress with a higher yield. For the case study, we have the one from the federal government of Nigeria, granted environmental approval for evaluation and open cultivation of Tila maize or new maize variety, genetically modified to tolerate moderate drought and resist fat animal and stem boreal. For the improvement of biotic stress tolerance against pathogen, climate change significantly alters the dynamic of plant pathogen, primarily through changes in temperature, humidity, and precipitation patterns, which can enhance the virus and spread of virus-prone disease. With CRISPR-based genomic editing technology, producing crops that can fight disease is enhanced. We have the case of the maize streak virus, the endemic to Africa and the major viral pathogenic concern to maize production, making resistance a key target for crop improvement. Scientists at the University of Cape Town and Panner Seed have developed maize resistant to MSAB. The other different constructive argument for the crop resilient climate, we have the herbicide tolerance crop that have genetic features that allow them to withstand certain herbicides. This allows farmers to spray herbicide to kill weeds without harming the target crop. We have also the insect pest control that reduce pest damage, chemical pesticide use, and mycotoxin contamination. For example, the case study in South Africa that growing GM crops since 1998 and it's the landing as the first African country to commercialize genetic modified crop through the Environmental Biosafety Cooperation Project. This was followed by Egypt and Burkina Faso and Sudan cultivating BT cotton maize. For the disease tolerance, we have using DNA markers associated with desirable tree breeders can select plant earlier in the breeding processes, saving time and money. Scientists have been using this technology to select lines with resistance to disease in order to prevent loss. The case study from Kenya Agriculture and Livestock Research Organization and the National Agricultural Research Laboratories are developing a maize that is resistant to maize leaf necrosis without altering desirable tree using CRISPR-mediated genome editing. As the negative team construct against this constructive argument, so we have to repose on of them. First, the critics argued that funding should be directed towards other agricultural innovations, for example, such as improved soil management, irrigation systems, or organic farm practices. Of course, these approaches have merit, but they are not sufficient to address the challenges posed by climate change on large scale. For the irrigation system, it can help manage water shortages, but don't address the root causes of crop vulnerability to drought. Also, soil management techniques improve fertility, but they don't enhance a plant's ability to survive extreme temperature or resist pests. Genetic research directly enhances the plant itself, making it inherently more resilient to harsh conditions. Another critic argument is that the initial investment in resilient crop may seem costly. The long-term benefits outweigh the expenses. We can say that rather than saying investment in resilient crop as an expensive cost, it should be viewed as a necessary and strategic investment for food security, economic stability, and climate adaptation. For the third critics is that it expressed the concern about the ethical and ecological application of genetic modification. But however, the modern genetic research does not solely rely on genetic engineering. Advanced breeding techniques, others like CRISPR gene editing and marker-assisted selection, all of which can be applied safely and effectively. Many successful projects, such as the development of drought-resistant maize in Africa, demonstrate that genetic research can be a responsible and sustainable tool for improving agriculture. If we take an example by 2013, we have 50% decline in crop productivity, but we can enhance this productivity by 2100 in 80% drop in crop incomes. So we can summarize the response to this negative argument as like this. So for the high cost of the resilient crop, we can say that cost is justified by long-term saving and higher yielding. And for the not accessible by the farmers for this crop resilient, we just say that we can implement public programs and also the traditional breeding can make these crops available to farmers. Other counter-argument is that not all of this, it's not a full solution to adopt crop resilient. We can say that this is a part of a larger climate adaptation strategies we can undertake. For the low adoption by farmers, we have just to raise awareness and educate farmers, and we have a lot of success stories that shows the increasing demand for these crops. For the test issue, so we can say that modern breeding ensures test improvement, And for the health risks, it's just we have to perform strict testing to ensure safety, and so far no proven case of harm is detected. The negative team argue that biodiversity is losses if we adopt crop resilient. Our argument is that the proper and good management can prevent the gene transfer from variety to others. For the regulatory challenges, where regulation are evolving for faster approvals, and for the unintended consequence of these crops, we can say that pre-realized testing can be performed to minimize the risk. And finally, for the short-term gain of this crop resilient, just say that we can implement programs that focus on long-term sustainability, not just for the short time. So as a closing statement, given the unprecedented climate challenges facing global agriculture, governments must invest in solutions that provide long-term resilience, economic benefit, and food security. Genetic research stands out as the most efficient and scientifically sound approach to develop climate resilience crops, surpassing other agricultural innovations in terms of sustainability and impact. While traditional methods remain important, they should compound, not replace genetic advancement. Funding genetic research ensures that future generations inherit a food system that is adaptable, sustainable, and secure in an era of climate uncertainty. Finally, government must act now by prioritizing genetic research. They can safeguard agricultural productivity, support farmers, and build a more resilient future for global food security. And thank you for your attention.